Hello my dear students, welcome back to DMG chemistry classes, and in this video I am going to discuss the relationship between different types of equilibrium constants. And in my previous video I gave you an idea about different types of equilibrium constants like Kp, Kc and Kx. And here we are going to derive very important and very useful relationship between these equilibrium constants. So let us derive the relationship between Kp and Kc first. And to derive this relationship, let us consider a general reversible reaction which is at equilibrium, in which A moles of A are reacting with B moles of B, giving us L mole of L and M moles of M. And I have also told you that this small a, b, L and M are also called as stoichiometric coefficients. And if the equilibrium constant of this reaction is expressed in terms of molar concentration, then its equilibrium constant will be represented by Kc, and Kc is equal to is L raised to power L into M raised to power M divided by A raised to power A into B raised to power B. And I have also told you that this Kc can also be written like this, that is Kc is equal to Cl raised to power L into Cm raised to power M divided by Ca raised to power A into Cb raised to power B. I'll add this equation number 1 and this equation number 2, and here the Cl, Cm, Ca, Cb are the molar concentrations of L, M, A and B respectively. Okay, and if this A, B, L and M are gaseous, then the equilibrium constant will be expressed in terms of the partial pressures and represented by Kp, and then Kp is equal to this Pl raised to power L into Pm raised to power M divided by Pa raised to power A into Pb raised to power B. And let this equation number 3. And if the gases, that is gaseous A, B, L and M, okay, so if the gases are supposed to be ideal, then we can apply the ideal gas equation here. And according to ideal gas equation, this PV is equal to nRT and P is equal to N upon V into RT. And this N upon V is the number of moles per liter, that is, it is the molar concentration. So let us understand it, that so if the total volume in V liters, so if in V liters we have dissolved how many N moles, then in 1 liter we will have N upon V moles. Okay, so this N upon V is the number of moles present in 1 liter, that is number of moles per liter. So it is molar concentration and it will be represented by C. So equation number 4 can be written like this: P is equal to CRT, where this N upon V is equal to C, that is molar concentration. So let this equation number 5. And following this equation number 5, we will have Pa is equal to Ca RT, Pb is equal to Cb RT, Pl is equal to Cl RT and Pm is equal to Cm RT. So now we have expressed the partial pressures of A, B, L and M in terms of their molar concentration. And now we will substitute the values of partial pressures in equation number 3. So let us substitute. So when we will substitute the values, then the Kp will be equal to, in place of Pl, now we will have ClRT. We will have here, that is ClRT raised to power L. Likewise here we will have Cm RT raised to power m divided by CA RT raised to power A into CB RT raised to power B. Okay, so now this is Kp, and let us solve it further, and the Kp will be equal to Cl raised to power L into Cm raised to power m into this RT raised to power L into RT raised to power m divided by this Ca raised to power A into Cb raised to power B into RT raised to power A into RT raised to power B. Okay, and further we will have Kp is equal to Cl raised to power L into Cm raised to power m divided by into the bases are same and the multiplication sign is in between, then the powers will be added. So we will have RT raised to power L plus m divided by Ca raised to power A into Cb raised to power B into RT. Here also powers will be added and RT raised to power A plus B. Okay, and Kp will be equal to this Cl raised to power L into Cm raised to power m divided by this Ca raised to power A into Cb raised to power B, and here RT that is the bases are same and we have division sign in between, then their powers will be subtracted. So here we will have into RT raised to the power L plus m minus A plus B. Okay, so here this L plus m is the total number of moles of products, and this A plus B, it is a total number of moles of reactants. Okay, so let us write it further. That is Kp is equal to Cl raised to power L into Cm raised to power m divided by Ca raised to power A into Cb raised to power B into RT raised to power Np. Np, that is L plus m is equal to total number of moles of products. Okay, so I have written here Np for the total number of moles of product, and likewise this A plus B will be equal to Nr, total number of moles of reactants. And I have told you in the beginning of this video that this quantity Cl raised to power L into Cm raised to power m divided by Ca raised to power A into Cb raised to power B, it is equal to Kc. So this quantity is equal to Kc. Then we will have Kp is equal to Kc into RT raised to power delta n. Okay, where delta n is equal to Np minus Nr, that is difference between the total number of products, total number of moles of products and total number of moles of reactants, where this delta n is equal to Np minus Nr. Okay, so this is the required relationship between delta n. Okay, this is the required relationship between the Kp and Kc, and if this delta n is positive. If this delta n, okay, if this delta n is positive, and it will be positive when total number of moles of products are greater than total number of moles of reactants. And when this delta n is positive, then Kp will be greater than Kc. And if this delta n is negative, and it will be negative when this Np is less than Nr, okay, and when it is negative, then this Kp will be less than Kc, okay. And if this delta n is equal to 0, and delta n will be equal to 0 when the total number of moles of products are equal to total number of moles of reactant, that is Np is equal to Nr. Then according to this equation, we will have Kp is equal to Kc into Rt raised to power 0, and anything raised to power 0 equal to 1, and then this Kp, then the Kp will be equal to Kc, okay. So now let us derive the relationship between Kp and Kx. That is relationship between Kp and Kx. So I am writing the Kp again. That is Kp was equal to, that is Pl raised to power L into Pm raised to power M divided by Pa raised to power A and Pb raised to power B. And if the concentration is expressed in terms of mole fractions, okay, then the equilibrium constant will be represented by Kx, that is Kx, and it will be equal to Xl raised to power L and Xm raised to power M divided by Xa raised to power A and Xb raised to power B, where this Xl, Xm, Xa and Xb are the mole fractions of L, M, A, B, A and B respectively. Understood? So this is the Kx, that is the equilibrium constant in terms of mole fractions. Now if the total pressure of the reaction mixture is equal to P, here I am talking about the total pressure of the reactants and the products, because this reaction will take place in a closed container, because the equilibrium is always attained inside a closed container, and that reaction mixture will have some total pressure. So let us suppose that the total pressure of the reaction mixture is equal to P. Then the partial pressure of the ith component, then the partial or individual, okay, so the partial pressure of ith component is given by that is, so Pi is the partial pressure of ith component, and it will be equal to Xi into P. That is, this partial pressure Pi, it will be equal to the mole fraction of the ith component into the total pressure of the reaction mixture. Okay, and from this equation we can write the partial pressures of our reactants, that is A, B, and our products L and M. So following this expression or this equation, PA will be equal to XA into P, that is the mole fraction of A into the total pressure of the reaction mixture. Likewise, PB will be equal to XB into P, and this PL will be equal to XL into P, and PM will be equal to XM into P. Okay, now we will substitute the values of these PA, PB, PL and PM in this equation, that is expression for the Kp. So let us substitute. Then we will have Kp is equal to, so here in place of PL I will write XL into P, that is XL into P raised to power L into XM into P raised to power small m divided by XA into P raised to power small a into XB into P raised to power small b. Okay, and from this this expression will be further written like this. It is Kp it will be equal to XL raised to power L into XM raised to power M into PL raised to power P raised to power L into P raised to power M divided by XA raised to power A into XB raised to power B into P raised to power A and P raised to power B. Okay, and it will be further equal to Kp is equal to this XL raised to power L into XM raised to power M into P raised to power L plus M, as I explained earlier, divided by XA raised to power A into XB raised to power B into P raised to power A plus B, and this quantity that is XL raised to power L into XM raised to power M divided by XA raised to power A into XB raised to power B, it is Kx. So this Kp, it will be equal to Kx into P raised to power L plus M minus A plus B, and this Kp will be equal to Kx into P raised to power, this is Np minus Nr, as I explained earlier, and this Kp is equal to Kx into P raised to power delta N. Okay, so this is the required relationship between the Kp and Kx. Okay, so now let us derive the relationship between Kc and Kx. So here relationship between Kc and Kx. So friends, we have derived the two relationships. first relationship is between Kp and Kc, and the second relationship is between Kp and Kx. And the relationships are, that is, Kp is equal to Kc into RT raised to power delta n, and second is Kp is equal to Kx into P raised to power delta n. These were the two relationships we derived. Now if you see these two equations, then their left hand side is equal, then their right hand side must be equal. Then we will have Kc RT raised to power delta n equal to Kx into P raised to power delta n. And from this equation we have Kc is equal to Kx into P raised to power delta n divided by RT raised to power delta n, and this is equal to Kc is equal to Kx into P upon RT raised to power delta n. Okay, and according to ideal gas equation, for 1 mole PV is equal to RT. Okay, and from this equation we will have P upon RT is equal to 1 upon V. Okay, now we will substitute the value of this P upon RT here, that is P upon RT equal to 1 upon V. Then we will have, that is, Kc is equal to Kx into 1 upon V raised to power delta n. Okay, and from this equation, after rearranging, we will have Kx equal to Kc into V raised to power delta n. Okay, that is Kx will be equal to Kc into V raised to power delta n, where V is the volume occupied by the 1 mole of the gas. Okay, and according to, or if we use the ideal gas equation for 1 mole, that is according to n moles. Okay, according to ideal gas equation for n moles, we will have PV is equal to nRT, and this implies P is equal to, or P upon RT, that is P upon RT, it will be equal to N upon V. Okay, and N upon V, as I explained in the beginning of this video, this N upon V is the molar concentration, that is number of moles per liter, and it will be equal to C. Then I will substitute the value of P upon RT, okay, in this expression. Then we will have, that is, this Kc, it is equal to, now P upon RT will be equal to N upon V, and N upon V is equal to C. So this Kc will be equal to Kx into N upon V raised to power delta N, and Kc is equal to Kx into C. N upon V is C, molar concentration, that is number of moles per liter raised to power delta N. So this is another expression between Kc and Kx. So here we have derived the different relationships between the equilibrium constants, that is Kp, Kc and Kx. So I hope that you have understood and you have enjoyed this video, and keep watching my videos and like and share my videos and subscribe my channel. Thank you very much.